Hi, I'm Dan, and I work at Stack Overflow on the internal engineering team. We support the sales staff and the infrastructure for our physical locations. And my talk today is your secrets in cloud-based key management services, or locks are for honest people. So if you're interested in the slides, I'll leave that up just for a second. You can go ahead and grab them. Some of them are somewhat kind of interesting, maybe. But so what does this talk about? There's 7 things going on in this talk. I'm not going to read off each one of them because I'm going to go through them as we go. I just like to give people a guide before we get going so you know where we're going to end up and when I'll stop talking. So how did we even start talking about this? Why did our team start talking about secrets and cloud-based things? And a little bit of background on it is we wanted to. This may come as a bit of a surprise, actually, but engineers, typically like to argue, and this talk, like any good talk, or this problem, evolved because we wanted to place things on services that we didn't necessarily own, or hardware we didn't necessarily own, and the pushback was, of course, you can't put X and Y. That's not secure. So the problem with this statement is that you can't respond to that. You either say, well, yes, it is, and the other person says, well, no, it isn't, and you don't get any real motion or movement with that. So you're really just stuck with a group of people who want to do something and a group of people who say, you can do it, but, just wait till that blows up in your face. It's not going to work out. So what I wanted to try to do and what we did as a team is we shifted that conversation to, you can't do that, that's not too secure, to how do you know if something's secure? And the question I like to give is, how do you know if your house is secure? And most people say, of course it is. I have a lock. And as many people, a couple laughs, yeah, locks are for honest people because, and this is a short, quick story. One day I was working in our New York office, and I had someone coming out to do electrical work on the house. I was prepared. I had a remote device to open my garage door so they could get in. I had instructions that I explicitly left, press the Ring doorbell so that I know you're there. I'll talk to you. I'll walk you through it. You can just do whatever you need to and get back out. The thing that I neglected to leave was instructions that said, do not turn the lock on the garage door. That is analog and will lock, and once you do that, I can no longer open the garage. Which they did. And now, the story doesn't end there. When I got back later in the day, my wife and I had moved into this house only a month or two earlier. We had never turned that lock before. We had no key, and that was the way in and out of the house because we just went through the garage. So no electrical work done, and I have no way into my house. So what do I do? Locks keep honest people out. That day, of course, I had to look for our back. If you get locked out, you look for your backup key. You break your window if you must. Hopefully, before you break the window, you pick the lock or some method of getting in because it's your place, you own it, and you just need to get through. So the answer to that question is really yes. My house is secure unless someone really wants to get in, and that's the problem with locks. Do you have data that you need to secure? And most of you will say yes. And if in case you said no, absolutely, you all have secrets. You might have API keys and passwords, config files, sensitive information that ends up in a repository, or worse, managed by hand outside of a repository. And how do we manage these? So most shops manage these things in a couple different ways. Like mentioned, we put config files in development and production. Only very special people get to touch those. The problems are it's visible in production, and files might differ from prod to dev. It wouldn't scale. If you needed to put these files on 100,000 systems and only very special people can touch them, that's going to be a really bad time. Plain text values stored in code. Great, it's in the repository. The value is wherever the code is. It's always going to work out, no problem. Except it's in the repository. It's in the history. It's there forever. Anyone with repo access can see your secrets. Makes it very hard if you want to open source that repository because you have things in your history that are no good. encrypted files that live in a repository. So this is where I think most kind of secret sharing ends up. And this is what we do for a lot of this stuff internally. Typically, we use a tooling called Black Box that effectively encrypts a secrets file and is stored in the repository. The unencrypted version of that file is never actually in or checked into the repository, only the encrypted version. Black Box does some other nice things like manage who can actually decrypt that file and allows you to add and remove administrators who can do that. But that's the best thing, right? Come on, it's encrypted. Like, what else could we possibly want? So, are my secrets secure? Yes, if I limit who can access the repository. Yes, if there's no engineers who can look at production copies. And yes, if I rotate secrets in the repository often. So I have solved my problem, and we're done. Yes, if everyone does exactly what they're supposed to, and I trust that they are because I can't verify it, is really the answer there, which is, again, not a great answer. So, to our problem statement. As mentioned, we use Black Box and Stack Overflow, but some of the problems that we hit with that are this. If an employee leaves, we need to update all encrypted secrets. We don't have any history as to when someone accessed that file last. We don't know if they have an decrypted copy locally. And we don't know, even if we do update the repository, we don't know if they will update the repository themselves so that now they've removed themselves as an admin from it. So it's a problem really of distributed secret management. So the end result is that the data is secure because we think it is, unless we go through and actually update all of it, because then it is secure. Again, the problem falls back to we trust that people are making good choices, which is great from the perspective that we feel we can trust each other, but not great from compliance and security because we're just hoping that things are the way they should be unless we're doing a tremendous amount of work to make them so. And then the end result, yes, the big problem is everybody lies, so we can't trust anyone. Or at least that's the safest perspective to take when wanting to ensure that we are complying with our security ideas. So this is a quote from an article on ISO.org. And when I was looking around to try to solve this problem of how do we deal with distributed black box issues, how do we deal with putting our secrets in locations that we don't manage, ISO came up quite a few times. I do not have a tremendous background in doing things with ISO compliance or anything like that, which is why when I looked at this, which is a section of a slide about how to do things, in an ISO compliance method, I was like, oh, this is really cool. There's so much, and there's no way that our team of like 5 or 6 people will follow this every time that we need to make a small change or update, much less grok everything that's going on here. So I tried to distill it into useful things. Risk, control, audit. These 3 things were things that I could take into a meeting, explain quickly, and then implement in a way that made sense. These are also things Equifax missed. So, controls manage risks. Risks versus controls, back to our home security question. Yes, my home is secure unless I forgot to lock it. Yes, unless someone knows about my secret key. Yes, unless it catches fire. So these are the controls that manage my risks. So the answer is yes, unless the controls fail. Auditing. Trust but verify. I know my house is locked because my smart lock reports it to be. My Ring camera lets me know if someone accesses the secret key, and my fire alarm goes off if the house catches fire. So then the audit-based answer becomes, controls are managing my risks, and here's my audit log to prove it. And in one of the earlier talks today, it was said so well that I wish I had it, but you can't verify security, but you can verify compliance, and that's kind of what's being hit on with the audit log here. So how does this bring us to a key management service, and why is this related? It's better than a lock. So if you're not familiar with a key management service, you may have a secret service of some kind internally, very kind of similar idea. This talk is focused on cloud-based ones, or effectively taking what is that secret service internally and handing it over to someone who is not you. And they kind of come in a few different ways. You have, your cloud-hosted, where the provider manages all encryption and keys, user-provided keys, where you reach out to the service with particular keys, or you manage the keys and just tell the service, hey, I need to verify if I have permissions to do this. Or user-hosted, you cut out everything, kind of like the internal secret service that I mentioned just a moment ago, where you are relying on a server internally that you manage to handle that. Some other things we like to see, or like key exciting features with a cloud-based service, the ability to rotate keys. So when I mentioned if a staff member leaves, then we can rotate our keys, or just because we want to rotate our keys periodically in case we have a stale key somewhere that we don't want to be able to access these secrets. Identity management. What's better than, if you have the key itself, you pretty much can do whatever you want. You can claim to be whoever you want to be. But an identity management piece is useful because now you have to verify that, in fact, the person or service accessing this thing is a member of a directory of users who may or may not have access to it. And an audit history, of course. Like as we mentioned, audit history is always one of the most important pieces for this to work. So we have a couple different providers I mentioned here. I'm not going to go into detail too much on each of them. We are going to look pretty closely at Google KMS, but AWS also has a key management service, and Azure has their Key Vault. All of them can essentially do these 3 points here, but they all have varying additional services and features that integrate more closely with whatever you're working with. So let's look at Google Key Management Service. So this is a function we're going to call build key, and this is kind of what everything starts out with when you want to start using Google KMS. If you've ever built any service on one of Google's APIs before, at the end of the day, you're essentially generating or using the build function to create a service that now lets you interact back and forth with it. In this case, we are listing a particular project where the keys for this project live, what the name of the key ring is, and then a name of a particular key on that ring. We're not going to go back and look a whole lot individually at all these things. I just wanted to get them out of the way once so that every time I use this build key function, you'll know kind of what's going on. It's just generating a key that allows us to talk to the KMS service. So at the very end there, we have crypto keys is essentially this client that we've built, and then it lets us work with crypto keys to do all the things that the crypto keys class can do. So in our first step here, let's encrypt something. We're going to say our key name is, we use our build key, and then we're going to just open a local file. We're going to take the text out of that local file. We're going to generate a request that takes that plain text, and we have crypto keys encrypt. We're going to say, OK, Google KMS, please encrypt this plain text that we've sent over to you and give it back to us. And we take that now encrypted text back, write it into our secret file, and it's encrypted. So right away, some people may look at that and say, I've just sent them the plain text. I've just sent them everything. This doesn't work for me. There's some other ways around that we'll talk about after I go through the whole process, but this was just easiest to explain and demonstrate. So bird's eye view, again, our local script is sending the encoded plain text. OAuth pass or fails that. It's going to then go to Google KMS, which passes us back the encrypted ciphertext, and we store it. This is probably what the contents of our encrypted file looks like, something like that. And let's decrypt it. So again, very similar process. We take a build key, we read in that ciphertext, we're going to generate our request. We send the request out, it hits the OAuth pass-fail, and then it passes back to us the decrypted information. And we're going to see what that looks like in a minute, but I wanted to talk about what is happening when it actually gets to KMS. So this is a permissions list, an example permissions list for a key set. If you're familiar with Google Cloud at all, this is their IM page that works for just about every type of resource that you can create on their site. In this scenario, we're saying that anybody on the IT team at Stack Overflow can access this object. This is set at the keychain level, or it could be set at the key level, where you say this key can be accessed by anybody on this team. You could break your keys out into read-only, write-only, whatever you want in that regard. You can break up permissions among team members. In this case, we kept it simple. Anybody on the IT team can access this one key that we use to encrypt and decrypt. This is the actual, from logging, this is the request for decryption. And you'll notice it's kind of hard to see. I couldn't make it, oh, it's actually not too bad. But so at the top there, we have a Cloud KMS decrypt request. It wants to use the IT tools all access keychain. And it shows that I was the one that made the request with a dated time. I blocked out some sections in there, but it'll show you what it was that I actually requested, not the clear text of what it was that it decrypted back to me, but I can effectively break these logs down to kind of see what it was that this person accessed and when. So we got our secret back, and it might say you can decrypt this. In our example, that's actually what it did, but it could also be something useful like keys, email addresses, secret codes, things that you might want to actually put in code later on. And as mentioned earlier, yeah, sending plain text will not work for a lot of people. What you can do in a slightly more complicated setup is you manage the encryption and decryption locally, and you only pass to them encrypted or plain text versions of the key to encrypt or decrypt that secret locally. So they never get the lock in this scenario. They only get the key at one point, encrypt it back to you, and you only pass around the encrypted key back and forth. And in fact, that's the way that Google's KMS service is really designed to work, because while you can send them anything, they will cap you at 64 KB, which was designed to allow you to just primarily send your keys back and forth for local decryption. For our use case, which I'll go over right now, we'll talk about that. Yeah, let's look at how we're actually utilizing this. So we have a library called IT Tools. IT Tools is a service that we use, that all of our scripting on our team relies on for onboarding, offboarding. If you want to interact with a service and do something a little interesting, like manage Google Groups in your own custom portal, all of that sits on IT Tools. So we had quite a few secrets in this library. And if anyone on our team ever left, there was a lot of changes that we needed to do to make this viable. So we created a new module in IT Tools called kms.py. So the first thing this module had to do is verify who it was. And we just do a little bit of OAuth here. A lot of our services are Google Smart, or we can use application default credentials. If you're not familiar with that, it's essentially certain services let you, or if you're running on App Engine or in certain compute services, you can say, hey, just know who this service is, or know who this script is that's running, and it can do it. We also had services that were not Google Smart, so we would just, in those cases, set an environmental variable that said, hey, if you find this, use these OAuth credentials when you need to auth. And in that scenario, we would inject that environmental variable in a way that we felt was secure in our build service or some other method of getting it onto the box. That was more of a one-off. We kind of preferred to rely on Google default where we could. So in KMSPY, once it verifies that it has OAuth credentials, if it has credentials, let's build a storage client. We're going to build a bucket request. What this does is it pulls an encrypted version of our secrets out of a Google Cloud bucket that we have a limited set of users and services you can access. So we pull down the ciphertext, and then if we do have ciphertext, we're going to build our key to decrypt it. So now we take the ciphertext, pass it over to the KMS service. KMS passes us back a decrypted version of those creds. And if, in fact, we do have creds, then we exec those into the running Python application. So what does this gain us? Our developers on our team never actually have to keep the secrets on their system. The secrets are decrypted at runtime, so they exist in memory. When the process ends, they're gone. And we have logging of every time that an encryption or decryption event happens. So this is what the actual, one of the files, say Trello.py would be where we kind of do Trello things, or the library that gets us Trello things. The top of the file looks like this. So we have a few secrets we want to pull in. First, it tries to grab the local creds file. That is our fallback. We still have black box as a failsafe in case KMS is down or some other crazy thing happens. As long as we have a decrypted version of the creds file locally, everything still works. Typically, we do not. We either leave it encrypted or we just don't put it there at all. So it fails over to the KMS.py file, effectively, where these secrets were read into memory. So they're there. It just they just work as if it was reading it directly out of a file. How often do we use this? We fully started using this on all our services about August this year. We have a team of 4 ISEs who access it daily. It's the same exact code, whether they're developing locally or running it in production. We have maybe about 20 services accessing this at any time. Like I mentioned, we have black box as our fallback. And so far, we haven't had a service failure due to KMS being unavailable, which has been pretty cool. It's pretty reliable, at least for our level of need. That list along the side there is just a screenshot of a bunch of the different services that we reach out to with this. So it's pretty heavily used on our team. So to circle back and wrap it up, we took the argument or the combative question of you can't do that, it's insecure or it's not secure, and changed it to this. What controls manage my risks and how are they audited? And again, to look at the things we talked about, personnel turnover is our risk. We control that with key rotation, and we audit it with the IAM policy from the KMS service. I won't go through each of those, but that's effectively reframing the question into a way that everyone can participate, use common language, and feel good about an outcome instead of yelling at each other until someone finally is tired of doing so. But that's it.
If you have any questions, please come up and use the mic for the benefit of the recording.
Hi. Sorry, maybe I missed this bit, but there has to be an access key to actually authorize you to connect to the KMS. So how do you secure that part?
Yeah. So the first time I did this talk, that came up too. And so there's two bits to that, right? So the access is really just based on identity. So identity is the OAuth portion, either your script or your user through like an OAuth. If you're developing locally with gcloud, there's like a cache set of credentials that verify your identity. And I know that doesn't answer your question directly about the actual key that you use to do the encryption and decryption, and that's because in this situation using Google KMS, you never actually get that key. You verify your identity, you pass the information over, the KMS service uses the key that you named, just a string name of that key saying, I want the all access key, uses the key that only they keep a copy of to encrypt the information and passes it back to you. The downside is you never have the key. So you always are reliant on KMS to do the decryption. The upside is key rotation is really seamless because when it says, oh, this was encrypted with this previous key, well, I'm going to decrypt it for you, and now, next time it's encrypted, we'll always use this next key version going forward.
Sure, I get that part, but how do you prove your identity to the KMS so that, it's not like everyone can just decrypt anything by passing a key identifier.
Right. That's managed in the IM page. It's not a great example with a screenshot here, but effectively the key and the chain itself are an object in Google Cloud, and you can say this group has the ability to access this key. They can only do read from this key. They can only do write from this key. You define the the name of it's at the name of the key level. You don't actually even get to touch the version numbers of the keys. All you can do is say use the next version of the previous version. Get that. Does that target the question a little better?
I guess my point is, do you have to put a secret on disk inside your virtual machine in order to authenticate with IAM?
Yep. So that's to this part here, where our example. Yeah. So we never actually put the secret on disk. We will put it in as an environmental variable to get the authority or the identity of the script or environment effectively making the request. And if it's running on, again, a Google Cloud Intelligent service, then we don't even need to do that because just like we would say members of IT team can access this, we can list the Google app email address of a particular service as being able to access that as well. So we effectively offload all of it to OAuth, being able to verify that such and such is able to access this resource.
Okay, it's a little bit clearer. Thank you.
Okay, thanks.
Hi, I think you partially answered my question, but I'm curious, how do you bootstrap the secret, right? So we know we can rotate it, we can access it. How do you automate bootstrapping of your secret?
So I left that piece out because it works really well, but the code is very specific to our particular key. We basically have a make file in our repository that has like encrypt secret, decrypt secret. And what that make file does is it looks for something very similarly named to our secret.txt in the repository. And that only exists if someone has successfully decrypted it against using the KMS service to actually decrypt the file, or if someone has manually actually dropped the file in there with the correct information. And then if you do the encrypt target in our make file, it takes that file, encrypts it, puts it in our Google bucket, and then it's ready to go.
Perfect. Thank you.
Sure.
All right. Thank you very much, Dan, for that excellent talk.
Thank you.